So I'm going to give a talk on IPv6. It's something that's been very close to my heart for over 23 years now. You'll remember me doing the tunnels back when I worked for UWA last millennium even. And if we've got enough time, I'm going to try and do a bit of role play with all of you, and we'll try and simulate it if we get time. So without further ado, there's the agenda. I just back this together quickly. Who am I? Well, most of you know me. Who actually doesn't know me here? Anyone? 1, 2, 3. Okay, half of you lied, and you just don't want to know me. That's fine. Right, what is IPv6? What is IP? The adoption we're seeing around the world, which, if you've not been looking at it, this has silently been growing. Use cases in AWS, limitations in AWS, and that role play if we get time. So, firstly, who am I? That's me. So I started using AWS in 2008 when I was living in London, quite a while ago. And obviously I've looked at that change that's happened in the ecosystem over the, what's that now, 14, 15 years now since then. Currently 8 times certified. I'm the longest certified solution architect in the world, mostly because it was a new certification when I worked for AWS in 2013. And Elliot, I think you were just a couple of months behind me, you would say? Yeah. Give or take. I also write the certification subject matter questions on the Pro and Specialty Certs and Associate Certs. Just finished that 2 weeks ago again. I've been an ambassador as part of the Partner Ambassador group since 2017. Last year I was the number 2 ambassador, basically just blogging away. And it was that blogging away that I think led to you reaching out and saying, do you want to give something on IPv6? Because there was a couple of new releases that happened on AWS pertaining to IPv6. Which has been stuff we've been talking about for quite some time. I opened the AWS office in Perth in 2012, so a decade ago, and I worked quite closely with the CloudFront team, firstly to establish a point of presence for CloudFront in Perth, basically pointing at a map and saying lots of latency here, and secondly trying to get IPv6 deployed on that, because even in 2012, it had been 14 years that I've been dealing with this lack of technology and the migration that we're slowly sneaking our way through. I now work for Modus, who are around the world, and Modus was Agilon, so some of you who've been in the industry for a while will remember Agilon. Agilon became Modus in 2018, and just for fun, we're going to rename the company again in a couple of weeks' time to Acodus, because that's what we do. And I've been a Debian Linux developer since 2000, so a fair bit of Linux and open source knowledge up here somewhere, mushed around. So what is IP? This guy, Vint Cerf, quite a legend. The best thing about Vint Cerf is if ever you get the opportunity to see him give a presentation, he's an engineer and he always does his presentations in a 3-piece suit. This is as good as I get. He basically defined the format for what we consider now as the IPv4 protocol, and thus the birth of the internet. He currently still works at Google, I think it is that right? He's been working on the next generation of InterPlanNet, which is a project to then build delay-tolerant networks that can scale the entire solar system and beyond. Anyway, he designed this protocol with 4.3 billion addresses, thinking that ought to be enough. It's all his fault that we're now having to change everything. But he's a lovely guy about it. So, a timeline of how these things evolved since the 1970s, when what we use now as IPv4 is defined, started getting major usage, and obviously the rest is history as to the birth and growth of the internet. There was an experiment with trying to change some of the configuration of what IP looks like, but there was a major flaw that means that IPv5 was never used. Anyone know what that was? It still had the same number of IP addresses. It's like, missed it by that much. So that died a death. Meanwhile, IPv6 came along, and one of the biggest things on that is that it can address a lot more unique hosts on the network. We've had to make do with a lot of shortcuts over the last 20 years or so on IPv4, and many of you would have come across NAT, Network Address Translation, and it's pretty much what your home internet router is doing. You've got 15 things at home on the network, but it actually all appears as one IPv4 address. And a lot of telcos have gone to the point now of not only giving you that one NAT, but a second one in front of that, because there's not enough addresses, and potentially another one in front of that. called carrier grade NAT. Now, just because it's got a fancy name doesn't mean it's good. It's actually a bad thing because you can't actually have clear communications between the devices. And also some of the NAT tables that remember that you were talking to him via me might fill up and therefore not function correctly. So, anyone know what that is?
Yeah.
Nick will know it. Yeah, it is a Nick.
Sure.
Very good. 10 base T, indeed. I made a 10 base T, 10 base 2. I made a very bad choice in my parents' house when I was a kid, and I actually wired it up for this. It was the wrong technology to back. But effectively, network Ethernet cards. What they do is they are going to format your data into an electrical signal that will be sent somewhere on a network. Now, that is low level. And what's inside that packet that is sent, or the frame of Ethernet data, is an IP packet these days. And there have been other protocols. Many of you might remember IPX, SPX, or AppleTalk, Token Ring. Yeah, there's a name I've not heard. Yeah, they've all basically died. They've not had the universal support that something like IPv4 has had. So, that Ethernet frame that you see at the low level link layer, it's got a header and a footer and then some data on the inside of that. Yeah? And that data on the inside of that is often the IP packet. And inside the IP packet, it's got a header and some payload. And inside that will be something that might be TCP or UDP with a header. And it's basically turtles all the way down. You're seeing that there's header and data. And inside that data, there's another header and more data. Until you get down to something that would be actually inside it, which is data, which might be something like an HTTP request or some other format of data that's in there. So it's encapsulation all the way up. Yeah? Okay. So I'm going to give you a little demonstration walkthrough of what that looks like. We've got 4 systems here. They're connected to 2 different networks. And this system in the middle here, I've designated a router. There's nothing special about it, other than if you go and buy a router off the shelf. It can be any system that can act like a router. It happens to be connected to both Ethernet switches. And so from this first client A, if he wanted to send an IP packet to C on a different network, then it's going to have an Ethernet frame that traverses across this first network to the router. And if you look at the source and destination MAC addresses that was on that, it matches the MAC address or the machine address, station address on the network as to where it would send through. He looked at that packet, unpacked those headers, looked at the IP inside, went, oh, that's due over there. I'm going to now pack you in a new Ethernet packet on the blue network and send you on your way. Does that make sense? And that happens again and again and again across the network so that your packet gets to a destination. And typically when you do a trace route, you'll find that the number of packets is detectable by the time to live, which is dropped out. So you can see this kind of stuff. The only place where that isn't happening right now is Russia, because all these links are being cut off. Right.
Joe, sorry, can I just go?
Yes.
So when client A sent it, you went to the router because
Yes.
that's where it knows to send stuff.
So he's got a MAC address on the local network. He's also got an IP address at the higher level. And he knows that his default gateway is that IP address.
Right.
And through discovery on broadcast on this network, he will say, who's got 10005 because that was told to me that that's my default gateway.
Okay.
And the response that comes back is 800020 blah blah. This guy here, he's your default gateway at the Ethernet level. Send your packets to him.
And then within the header was the address of the destination.
The destination. That destination there is over. In fact, I've gone one too far, I think. Go back, go back. That destination there is that guy. So as he unpacks this packet, he then replaces it into a new Ethernet frame onto this network. Yeah? Now there's some very cool stuff inside switches if ever you pull one apart. One of which is, it might be one network, but it actually works out by looking at the broadcast of these addresses, who's where and where the traffic should go. And that was a major difference 20, 30 years ago between hubs and switches. A hub was not smart. If you sent a packet in here, it would send it to everybody. Yeah? Which basically chewed up your bandwidth on your network. A switch goes, hang on, you said that address, I know it's out that for, so I'm only going to put it out that link. And it happened automatically, transparently, nobody had to configure anything. It's quite smart in that way. It just was more efficient. Okay, thank you for the question.
All he knows that.
Sorry?
All he knows.
How does he know that? by listening. It's like, if you listen long enough, everybody sends a packet out, and you're always going to have your source address on the packet, the Ethernet frame you send out. So just listen and you'll work out who's where.
It creates a lot of traffic.
No, it reduces the amount of traffic. Because as you listen, you realize that this source is out this link, and this destination is out that link. So if I see a packet that comes in for that destination, I know not to send it to everybody else. So it reduces it. And didn't require any smarts on this end.
But this redundant sign-off saying, I'm here, I'm here, I'm here, I'm here, causes traffic.
Well, no, it's not actually another transmission to say I'm here. It's just the traffic you're sending anyway. You're already sending something. What time is it? What's my DHCP lease? The packets you're already initiating. Cool. So, so one of the things that's changed a lot, and you don't need to understand the details of this, but this is what basically an IPv4 header packet looks like. And of course, you've got a source and destination on the internet, and you'll recognize what they look like because that's the dotted quad numbers of 130.95, 128.2, or whatever that happens to be, that you'll recognize as source and destination. Now, I've got on the left-hand side, this is just from Wikipedia, on the left-hand side is the number of octets of bits that we've got in that source and destination. So, if you count between 12 to 16, you've got 4 bytes. 4 8s are, thank you, yes, 32. So you've actually got a 32-bit address space, which is what translates to 4.2 billion unique combinations of those bits. But you've also got a whole bunch of other stuff at the top here, which was a great idea in 1976, not all of which is used today. In fact, the fields are defined and some of them are just 0. They're not used. You're sending data which is irrelevant because that's the standard of the packet. So some of that has been optimized in IPv6 to go, you know what, if it was optional, we don't need to send it. We'll actually save some data on the network, which adds to some efficiencies. Funny story, one here called ECN. If that flag is set on a response packet across the internet, it's that the server that sent you that is saying my network is congested. It's the explicit congestion notification flag. And that only started being used about 2001, 2002. And of course, what happened at that stage is most routers that they see a new flag being set here should ignore these new things. I don't know what it is. Fair enough, just send it on. Unless it was Cisco, in which case what Cisco did was just go, what's this packet? I'll drop it on the ground. So it was really easy to spot who had a Cisco PIX firewall sitting in front of Bankwest, any organization, because they were just dropping traffic if that congestion notification packet was set. Really fun. Okay, so your payload would be after this, but if you look at the size of these two lines here of source and destination, compare that to what happens when you move to IPv6. Much bigger. So here we've got actually 128 bits of addressable space. It becomes a lot more. But also the headers here have simplified. You've got this idea of a next header. Well, if there's a next header for me to send, then I'll add it. If there's not, there's no next header, which has obviously truncated down the amount of data that we're going to transmit on the network. Does that all make sense? Now, you can use Wireshark to pull all of this apart and see it. It's really boring. But that's a quick summary of, hey, this is how things have changed and how they've thought through how can we be more efficient on the network. Right, 300, yeah, as it says down the bottom, 340 trillion addresses. We're unlikely to use all of those, but demand has been going up above 4 billion, so let's not hold our breath for too long. So if we've got a network set up and we've got a couple of clients on this site, one is on the IPv4 only network. He can speak to an IPv4 server just as you do now. If you've got an IPv6 client who's only on IPv6, he can easily talk to an IPv6 server. Yeah? They understand the same addressing topology. If you've got a server a client which is dual stack, it's got both addresses, and that is completely legal. You can have an IPv4 and an IPv6 address at the moment, and some of you in this room on your phones right now already do this. You can talk to either. Doesn't matter. Now they technically would be two separate networks. They're abstracted away by the IP protocol, but you can talk to either using either your IPv4 stack or IPv6 stack. And of course the server on the other end itself could be dual stack, so it doesn't care. And in fact, what you end up with after you've been playing with IPv6 for a while is it's so boring, it's uninteresting, and it doesn't matter. It is just a transport protocol. It shouldn't adjust your security posture. It shouldn't be too much different in any latencies or efficiencies, because the size of the address versus the header optimization, it comes out about the same. But what's interesting is trying to get an IPv6 client on the new internet to talk to a server that doesn't understand it. And it can be done. And here is the trick. So inside AWS, there are a couple of new releases that have happened in the last 4 months or so, being called 6-4 DNS and NAT 6-4. Okay? Now, you're probably familiar with a VPC. Anyone not familiar with a VPC? They know what a VPC is? Good, good. I'm in the right room. Okay, so you know that you have a DNS resolver endpoint that can answer your DNS queries. Where is www.flux.com? Here is the address. And there's a couple of types of queries that happen on that, but let's just start with that. Your client can ask the VPC resolver, where is that? And the address will come back as you'd imagine. But actually what you can also do is you can nominate now that a subnet inside your VPC can have a forged address sent back to you. Ooh, forged? How so? Well, instead of giving the real answer, we can lie to you and give you a fake IPv6 address. So let's say that we've got an IPv4 server and its address is, I'm going to use 130.95, it's the old UWA range, 130.95 1.1. But you don't understand IPv4 because you're an IPv6 only client. So this DNS will go and find out that address, come back with the IPv4 answer, and then fake up a special IPv6 address to tell your client you need to go to this destination on the IPv6 network, which will end up on a NAT device, receiving your IPv6 packets and translating them to IPv4.
Don't you get into spoofing territory where you can, it becomes exploitable?
Why do we get into spoofing territory?
Yeah.
In what sense?
Like, because you're doing a fake address and giving clients.
Well, the fake addresses are all within the same range, and inside your VPC, you set up a routing table that says for that entire network range that is the fake address range, send it to my NAT gateway. Never out the front door. So you're only spoofing it within the context of your own network.
Ah.
Yeah? You're not spoofing it to a packet that actually goes out the front door as an IPv6 packet. So this allows effectively backwards compatibility by doing that. Now NAT has been one of these things that has been frowned upon for a long time because of these performance issues and reliability and abstraction away of clear end-to-end connectivity. But in this case it's useful for, I've got to go IPv6 only for a reason of which I'll come up in a second. But some external dependency hasn't kept up with me. They're still only doing IPv4. I like to put this as, we've upped our standards, up yours. And of course, they're always a little bit behind on doing this, so we're going to need some kind of compatibility layer between these networks. Of course, you might just put 2 addresses on here. You might have a proxy server somewhere else in the network that accepts a request and makes a fresh request for you. There's a few ways to crack this, but 6-4 will work with any protocol, not just HTTP. Okay. So now you've said a few little bits and pieces that are in there. Why are we doing this? People keep breeding. We seem to be getting a lot of people around the place now, since 1050 or so. That's not this morning, by the way. There's 7.7 billion people in the world now. Since 1960, that's up by a couple of billion. Those people now also have more mobile phones. So we're hitting 8 billion mobile phones. We've already gone past the 4.3 billion IP addresses we were talking about previously, and not all of those IP addresses are actually usable. But it does look like a curve that's flattening a bit there. Who knows, there's probably going to be a new iPhone release soon and we'll be off to the races again. And on top of that, more people and more of a percentage of the population worldwide, the line is the percentage of the population using the internet. So adoption is driving this left, right and center. Any questions on those? No? Okay. So next is, who's actually using IPv6 anywhere? Because I've never heard of it. This is Google's graph from Monday of their traffic that they see worldwide on average that is IPv6 versus IPv4. Now it goes back some 10 years or so, but you can see we're clearly exceeding 35-36% of traffic worldwide is on IPv6. It's slowly being introduced. Now, you might not have noticed it, but that doesn't mean it's not happening. Now, there's another map which you can zoom into, which is the adoption per country. So in Australia, that adoption is hitting 27%. We're not that far away from the global average. On top of that, the impact on using IPv6 is seen as nothing. Now, some countries where the connectivity for IPv6 means that your network traffic goes the long way around, as opposed to an optimal route, you may see a negative impact. And in others, you see a positive impact from all this. In the wash, it ends out about the same. And this number, as you saw, has been increasing steadily month on month. So, 27.3% of the Google Internet traffic in Australia is already IPv6. Anyone here got a Telstra phone? Excellent. Could you please Google My IP from the browser on your phone? Assuming you're not on the Flux Wi-Fi. Anyone got Boost? No boosters? They also use the same ASN, I think, as Telstra does. And you should come back with an IPv6 address. Yeah? Okay. It's about 4 years now since Telstra activated IPv6 for their consumer market for all of the subscribers, working around it. Now that's because Telstra aren't the cheapest of carriers, but they do have some good engineers, and they've done that. There are other carriers who just haven't invested in the engineering to do that, so they're still relying upon IPv4 NAT and carrier grade NAT beyond that to annoy us. They'll get there eventually. So also some of the ISPs in Australia have also stepped up to do this. So Aussie Broadband, who I've been using now for about 2 years, have it as a tick box to turn on. Exetel, Internode has done this. It was one of their key points for using Internode out of Adelaide for a long time, and probably more ISPs over time. Telstra does? It's automatic. It's unremarkable at that point. Very good. So what are some of the use cases in AWS? Why would you want to? So on internet-facing services, you might want to offer dual stack connectivity to your external clients, because some of them might be coming across Telstra IPv6 or another ISP's IPv6. So instead of actually having that silently fail and fall back to IPv4, there's no additional cost to turn this on and make that available. At which stage, it's become a very boring conversation. It's just a transport protocol. You might want to use it on CloudFront on your CDN. Again, same reasons. There are 2 steps to do to enable CloudFront for IPv6. One of which is to tick a box that says enable IPv6 in CloudFront. But that's not the end of the story, and a lot of people stop at that point. The second piece is you do need to add a second DNS entry, what's called a quad A record, which is an alias to your CloudFront distribution. You might actually want your organization's DNS to be reachable over IPv6, in which case use Route 53 because it's done it for a decade. Or put it on instances, so it's directly contactable over the internet over IPv6. You may not want to do that. Yes?
Sorry, can I ask a question? So,
Please, Ben.
So we do use Route 53.
Yes?
So if we put the actual Route 53 connections
Yep. So query, there's 2 things. If I query your authoritative domain name, then I can actually currently do that over IPv6, even though the response that comes back is that your website is only IPv4. There's 2 parts. The response that comes back could be both IPv4 and IPv6, or it could be IPv6 only, which is unlikely at this juncture. Probably in another 10 or 20 years, it'll be commonplace. But yeah, there's very little to do there. But there's also this interesting point of what about inside my VPC? Has anyone here ever designed a VPC address space? Few. You've got to allocate how many addresses are in each subnet in an availability zone. What if you made it too small? And then you have to re-IP it. It's a very painful process. Well, there was a release about a month ago which allows you to have subnets in a VPC which are IPv6 only. Now, you can't choose the size of an IPv6 only subnet. It's 18 trillion. That ought to be enough. Let's come back in another 20 years and see if that was enough. You can have up to 255 subnets. There are allocations you can do either from Amazon's address space of IPv6, which is by far the easiest, or you can bring your own if you've got existing allocated address space. But that's a great use case where you want to spin up hundreds, thousands, millions of instances on analytics jobs that might be short-lived of a couple of minutes or hours, but your existing configuration of a VPC only allocated 64 IP addresses. So you can get around that with an IPv6 only subnet. Lambdas? Yes. Yes. I mean, they did optimize some of that by having multiple lambdas use the same ENI in a subnet.
Yeah, well, that depends on the size of the size of the lambdas, how many share of ENI. They
Yeah.
control over that. If you want something that's basically infinitely scalable and serverless, you're going to run that just basically on VPC only.
Especially the reuse of some of those IPs, then there might be a hold off that, hang on, there was a Lambda invocation that went off 20 minutes ago, it got this IP address when it accessed my VPC, and maybe I can't reuse that for a period. Now you might find also that your integration partners that you work with are migrating to IPv6 as well, so if your hosts themselves aren't on the IPv6 network, then you're going to be falling back to IPv4, and they're going to be having the same conversation with you that I have with some of my integration partners, which is, we upped our standards, could you please move forward, because we're trying to get to better than where we are now. Any questions on those? Nick?
Matt, my laptop.
Sorry, louder?
Is that a /48 public Amazon address space?
Yes.
Right.
Public address space. Now,
Yeah.
there is no private address space. Really, there's link local, and that is where your instance metadata server runs. In fact, that was another release that's happened recently, was for those of you that are familiar with running instances in a VPC, there is a concept of a metadata server and a time server, and of course that DNS resolver we spoke about, all three of which have now got IPv6 addressable endpoints within your VPC that you can connect to. So you can get to a IPv6 only subnet with millions of services, and most things still work. There are a few limitations. I've already spoken through all of that. So look, before I go to the limitations, things you need to do. So for example, this is the second IP address or DNS entry that you would have to make for a quad A record pointing to a CloudFront distribution, so that your CloudFront is both IPv4 and IPv6. Yeah. Now there's no additional charge for the number of records you've got in Route 53. There's no additional charge on CloudFront for enabling IPv6. So you either turn it on and have it done, or you don't. This is making a VPC. You can have Amazon provided address block, as you just asked me. Or you can take it from your own private address ranges. And then when you're making subnets, you can add, I think I had it over here, whether it's got an IPv6 address block for each subnet or not. You don't have to. I typically, these days, have been applying IPv6 to subnets for the last 4 or 5 years, because there's no reason not to. Security groups might still be closed. That's a separate conversation, but the addressing is done. There we go, IPv6 only. This is straight from the console. Easy stuff to get through. Of course, once you've worked it out in the console, you template all of this up and have that management of your VPC over the longer term from a template. And you can see the route table that we have here. There is this concept. In this case, I had 2406 : something was the address. So the addresses do look a bit different. They're obviously a lot longer, but that's the local address inside the VPC. Load balancers. So if you're using a managed load balancer from Elastic Load Balancing, they can either be IPv4 or dual stack, both address types. Obviously, you can only have a dual stack load balancer in a subnet which has got both IPv4 and IPv6 addresses available. And that can be for internal or external facing service delivery. For an A or B, the second thing you need to do is add this if you want it to be open for traffic. So this rule here is allowing HTTPS from the IPv6 internet and the IPv4 internet. Again, if you don't do both steps, you can turn this on, it's serving IPv4 traffic, and the IPv6 can't get in. So it's actually really easy to adopt these things in a very steady pace, enabling addressing on a VPC, addressing into a subnet, dual stack for a load balancer, before any traffic can get in because you don't open the security group. Christian?
The impact to internet gateways?
Very good question. An IGW can support IPv4 and IPv6.
Does it cost more to support IPv6?
No additional costs.
Good, because
No.
it really costs a lot.
In fact, the only thing is, obviously you know NAT Gateway. NAT Gateway has a reputation. Would I be right? Anyone here follow Quinny Pig? Yeah, he kicks it all the time. I'm so pleased I don't have the AWS. So it has a reputation, but obviously it's got a lot more useful with 6.4 translations in there. But no, there's no additional cost for any of this. This is for a load balancer. Well, it's pretty much the same thing. You need 2 addresses for it if you're going to serve IPv4 and IPv6. So there's a whole bunch of stuff that works out of the box. Again, no additional charges. So the metadata service that I talked about, and I would suggest that you look at the metadata v2 enforcement, something that we've spoken about a fair bit. The time synchronized service also is available, as I mentioned before. It's just NTP effectively. The DNS resolver. But there's another new internet gateway. There's what's called an egress-only internet gateway. Kind of like, if you think of NAT gateway, only allows my outbound connections, but it's also doing translation. It's a one-way diode. So you might have a subnet where the hosts are allowed to make outbound connections, but you don't want inbound. Now you'd secure that in 2 ways. Firstly, your security group would be closed, but secondly, your route table would point you via the egress-only internet gateway. Again, no charge for that. It's a configuration option effectively at the end of the day. VPC gateway endpoints, so S3 endpoints for your VPC, and of course transit gateway and direct connect all supported as well. Moving on. Not quite there yet. So once you're thinking, wow, I can have 20,000 servers all connecting to my database. Nah, work in progress. It might be though that your workload doesn't talk to RDS from 20,000 EMR nodes. It talks to S3 and then it puts a result in S3, in which case your problem is already solved. These things I'm sure will be improved over time, especially if we keep talking about it and sharing the video online. Hey, service team. So, effectively, it's really easy to get started with this stuff. It's very low risk. I've done this to production networks while traffic was going through it, no issue. Your mileage might vary, but over the last 5 years, we've not seen major problems from this over time. But I think you've seen something, haven't you? No?
Yeah, I can talk about it if you want.
Yeah, go on.
Okay, so there's limitations around the direct connect linkage with transit gateway, for example, where the association is limited to only 20 prefixes. Right? You can't have more than that. So what that means is if you've got a large enterprise, a lot of VPCs, and you've got your IPv6 VPC ciphers from Amazon, they'll all be
Random.
Random. You try and enter all those into that gateway, absolutely no way. It's broken. You can't do it. So if you're going to start using IPv6 in your VPCs, I recommend doing a BYO IP, get the big allocation itself that's contiguous, and then you future-proof it.
There's a lot of strategies with IP address allocation, and obviously there is now also a service for doing IP address management inside AWS. But having strategies where you've got contiguous networking addresses, so you can actually aggregate them together and address them as one bigger block, means that you can still fit within that 20 limit. So there's a few things to play with in there still. That's very good. Thank you, Steve. Yes, I've forgotten that one. Okay, so getting to the summary bit, and I said about 30 minutes, so we're almost there. IPv6 has taken over 20 years to get to this point. So in 1999, I was having to tunnel IPv6 traffic over IPv4 to Hurricane Electric when I was working at UWA. It was very limited and there was nothing on the IPv6 network at that time, so it was like, now what? But these days, because of CDNs, there's a lot of stuff that you're going to find is on IPv6, a lot of Netflix traffic, for example, because they're looking at how can they be more efficient on delivering that traffic, and other streaming content providers as well. By and large, there's no additional charges for most of these things. Obviously, a NAT gateway does have a charge, but you may already have that in your environment anyway. And it does become just a transport protocol. If you're still doing encrypted traffic on top of IP, we're all doing encrypted traffic because we don't trust anyone yet, which is the right thing to do, then your encryption is going to be just the same. In fact, that's another topic that we could talk about lifting up the level of encryption that you're doing. Does that all make sense? Okay. A few people asked me about this, so because it's fun, we rebranded obviously from Agilon to Modus in 2018, but we're now rebranding again because we bought another company of a similar size. So we're about to become a CODIS, which is marketing genius. Yes. Wow. We did manage to get the logo on a Formula 1 car last weekend. Did anyone watch the Bahrain Grand Prix? No? We've been doing some stuff with them. We were actually doing a couple of analytics projects with Mercedes in Formula 1 and Formula E for the last couple of years. Really interesting stuff like real-time translation and conversion from speech to text of the radio communications of the drivers and other stuff. We are hiring, obligatory, so yeah, but we're all hiring, aren't we? Loads of roles. Thank you very much.